today I'm going to talk about the flash memory, so let's start. First, let's talk about the basic schematic of the flash memory. So, you can see this picture. So, first, there is a multi-layer on the source and drain. So, this is charge trapping, like floating gate and charge trapping layer, and also the gate. So, and between of them, the oxide is located. So, at first, when you put some bias on the gate and the drain and source, the channel will be made, and then the electron will flow. So, when electrons flow the channel, because of the gate bias, the electrons move to the charge trap layer. So, yes, just you can see the charge trap means that. So the charge trap layer traps the electrons, and then it means the data is written. So, in this, under the picture, under the schematics, we can see the energy band diagram. This square, it means oxide, and then the line is the energy band diagram. So when the electron tunneling the oxide, and that electron can be trapped in the between of the oxide, and then yes, this means the Fowler-Nordum tunneling. And then when we want to erase the data, we can put some gate bias to the device, and then we make the electron go out tunneling the oxide, and then we get away that electron. So the electron will come back to the channel, and then it means the data is erased. So this is the basic schematic and the diagram of the flash memory. And let's talk about the VT of the flash memory. So when we want to write a data on the device, the VT shift will be like this. When we put some charged electrons to the charge trap layer, the VT move to the right side. So when we set the read bias before, so when we put the read bias and then analyze the current of the device, if the device current flows very well in the read bias, that device is not written. However, when we put some read bias to the device, but no current flows in the device, we can think that device is not written yet. So this is the critical critical characteristic of the flash memory. So we can think the written and unwritten state based on the current flow. So this is the flow, and then this is the NOR and NAND memory base schematic. So we can check the critical difference between the NOR and NAND. the left side is the NOR schematic of NOR. So every cell is individual, but however, the NAND flash is not. They are grouping each other. So the NOR gate is more fast, but it is hard to make smaller device based on the NOR, because the NOR wants every individual word line and bit line. So we cannot make a very smaller device based on the NOR. However, the NAND flash memory, they are grouped each other, so we can group. So this can just same word line and bit line, so we can make a smaller device based on the NAND. However, because of we cannot access individual word line and bit line, so writing the data or reading the data is a little bit slower than NOR. However, we can make a smaller device based on NAND. So nowadays we use many NAND gates in nowadays. So this is the data memory. We can make a single level cell and multi-level cell and triple level cells. So we can trap the data more, write data more to advanced technology. So nowadays, in the same VT margin, we can divide many steps to the VT distribution. So we can make more state and more written state, yes, to save more data. So actually it is very hard technology to make, because we can divide very many VT distribution. However, nowadays engineers make those technology to save more data to the device. So nowadays, saving more data is very important. So we should make smaller many VT distributions. So this is the VT window. So actually color this is the VT window, so VT margin, and then the max tail and the min tail between this margin, we should make a bigger VT window in here because we want to save more data. So we should make a bigger VT window and the smaller margin each side, and then we can save the more data than before. So today I talk about the flash memory. So thank you for watching my video. Bye.